Our next talk is by Michal Garlik, and he'll tell us about the weak rank principle.
Thank you. This is a joint work with Světoslav Krznov, Hanil Ren, and Idot Samerit. What is the weak rank principle? So consider a matrix product, x times y equals a, where x and y are matrices. These are variable matrices. X is an m by an n matrix, and y is an n by m matrix. And on the right-hand side, we have an m by m matrix, which is a constant matrix. So its entries are field elements from the field over which we consider this expression. Now, the weak rank principle says that this set of polynomial equations is unsatisfiable whenever m is greater than n and whenever the rank of a is larger than n. Of a particular interest to us is the regime where m is arbitrarily larger than n. So as the gap between m and n grows larger and larger, the proof system becomes weaker and weaker. And that's why we call it the weak rank principle. Also of a particular interest is the two-element field as the underlying field. And I will explain in the continuation why this is so. Notice that this is quite a general algebraic expression. It generalizes the odd-town theorem. The weak rank principle generalizes it. So odd-town is x times x transpose equals identity matrix. So if we obtain it by specializing, by substituting the matrix x transpose for y and the identity matrix for the matrix A. It further specializes if we add axioms imposing that there is at most one 1 in every row of the matrix X. So these axioms look like this: xik times xil equals 0. This is a work in proof complexity. The proof complexity has a goal of proving superpolynomial low bounds for stronger and stronger proof systems. In our paper, we consider several algebraic proof systems. Here I will define only one for you. So polynomial calculus resolution over the two-element field is the proof system which we are interested the most. And it has lines which are polynomials in the variables x1 to xn, and they are twins. Inference rules are the following. We can add two polynomials. So f and g, we derive sum of f and g. We can multiply a polynomial by a variable. Then we have Boolean axioms to impose Boolean values for our variables. And we add complementarity axioms, which say that the x bar is the negation of x. A refutation of a set of polynomials f1 up to fk is a refutation of the constant polynomial 1 from these starting polynomials. And it serves as a certificate that these polynomials don't have a common Boolean 0. Motivation for our work is at least threefold. First, the regime where m is arbitrarily larger than n requires the development of new low-bound techniques. This has been the case for the weak pigeonhole principle, and the same is true for the weak rank principle. The second motivation is so-called generator approach to proof complexity, introduced by Krajicek and by Alichnovich, Ben-Sasson, Borov, Wigderson. Of particular interest to us are proof systems like PCR over the two-element field, more generally proof systems where systems of linear equations modulo 2 are easy, and when where the weak pigeonhole principle is either easy or not known to be hard, which is the case for PCR over two-element field. The third motivation is to establish the hardness of circuit low bounds. Circuit low bounds is something we find difficult as people. It is conjectured that it is hard to prove them also in some formal proof systems. And circuit low bound formulas have been extensively studied in the mathematics of complexity theory. We make progress on all the 3 points mentioned here. First, to explain this generator approach, what is a proof complexity generator for a proof system P? It is a circuit mapping n-bit strings into m-bit strings when m is larger than n, such that the statement that a string B lies outside the range of G does not admit short proofs in P for any string B. Rasborov conjectured that with good enough parameters, Nissan-Wigderson generators are proof complexity generators for extended Frege. That's why this program is interesting. How do we view our generator or our rank principle as a generator? So it's simple. Matrices X and Y form the inputs. So we have 2 times n, many input bits. And the output is m square bits. X times y equals A. So what is the role of the matrix A? It is the role of this element B in the definition. So we are proving statement that A lies outside the range of the generator. Good. So in this algebraic form, X times Y equals A, the generator was also already considered by Krajicek in a short note, but he only considered it as where the measure of complexity is the degree of polynomial calculus, whereas, as you can see, the definition asks for proof size as a measure. And that's exactly what we investigate in our paper. So some previous results very quickly. So this is the paper who introduced the generators. They proved that there are proof complexity generators for polynomial calculus for fields where the characteristic is not 2. And also the stretch was not good enough to obtain applications like hardness of circuit low bounds. Krajicek defined a generator based on the pigeonhole principle. For AC0 Frege, it doesn't have good enough stretch. Razborov made the most significant progress in this direction. He proved that Nissan generators, a certain variant of special case of Nissan-Michelson generators, is a proof complexity generator for RSK and a PCR over F, where the characteristic of F is again different from 2. And he was able to apply his generators to obtain the hardness of circuit low bounds for these 2 proof systems. But again, the case of characteristic not equal to 2 is left open. That explains why we want to concentrate on that, those fields, or the 2-element field in particular. From the recent result of Kaniki, construction of a generator for AC0 Frege, however, the encoding prevents it to be applicable to circuit low bounds, to the hardness of circuit low bounds. So I will summarize our results first, and then continue to more detailed explanations, if time allows. We show that this rank principle is indeed hard for various proof systems, including polynomial calculus resolution over the 2-element field and Shirley-Adams. We use not only the algebraic encoding, which you have seen, but also 2 different CNF encodings. I'll describe one of them on the next slide. Then we iterate these generators to increase their stretch. So achieving the stretch up to 2 to the m to the big omega of 1, such generators are called function generators. And these are the generators which are useful to obtain the applications, like the hardness of circuit low bounds. And that's the third point. So we obtain hardness of circuit low bounds for the polynomial calculus resolution over the 2-element field. Briefly about the techniques. So we need to introduce several relaxed versions of a degree of a polynomial, because the standard, the classical notion, does not simply work. Together with this, we have to couple it with some random substitutions. Their role is to trade a proof of a small size for a proof which has a small relaxed degree. And these differ from standard random restrictions that just set 0 and 1s. Our substitution also have to substantially substitute variables, other variables, negation of other variables, or some small polynomials for variables. Final point I want to mention for the techniques is a design of a novel family of distribution on partial assignments, which is effective against Shirley-Adams. And in particular, it violates PHP. It's not useful for PHP, but it's useful for our rank principle. Okay, one of the encoding we use is bamboo tree encoding, we call it. And remember, the axiom, or each axiom of the rank principle says that a row of the matrix X times a column of matrix Y equals a matrix element Aij. So we want to, this big parity, this fan-in n parity, we want to replace it by fan-in 2 parities. And we do it in this completely unbalanced tree fashion. For this, we introduce 2 sorts of fresh variables. First are the Z variables to encode the degree 2 monomials, and then we add them one by one. So these variables use basically encode the prefix sums of the Z variables. We impose that the uppermost, the variable un is equal to the corresponding entry in the matrix A. And we have the axiom encoded as a CNF if you rewrite the parity as a CNF. Good. So this is the encoding which is most useful for applications. So the first low bound we prove is the theorem which says that for arbitrarily larger m than n, and for arbitrary matrix A on the right-hand side, polynomial calculus resolution refutations of the negation of the weak rank principle require size 2 to the omega of n. So this is a very strong theorem. The low bound is exponential. It does not depend on m. And the matrix A on the right-hand side is completely arbitrary. We then, well, as such, this is already a proof complexity generator, but it has almost quadratic stretch only, but it's still better than anything which was known before. We amplify the stretch by iterations, achieving the stretch of function generators, so 2 to the m to the big omega of 1. And these together resolved the problems, open problems raised by Aleknovich, Ben-Sastor, Razborov, and Wigderson, and by Razborov 2015, concerning the construction of such generators for the two-element field in particular. The application of the second theorem is the hardness of circuit low bounds, again in polynomial calculus resolution over the two-element field. So the statement in blue that some Boolean function f can be computed by a circuit of size s, we can write down as a formula. If a proof system refutes it, it means that the proof system proved a low bound, right? And we proved that polynomial calculus resolution over the two-element field requires exponential size to prove the circuit low bound, where f is an arbitrary function, arbitrary Boolean function, and s is a suitable polynomial in the number of input bits of that function. This resolves another open problem posed by Razborov in the same paper. Finally, a few words about the strength of weak rank principle, because so far we have considered low bounds only. So now we want to use it in a theories of bounded arithmetic to prove other interesting theorems. So we draw an analogy with what happens with the weak pigeon principle, especially with the theories of Emilie Řápek for approximate counting, where he bases his theories by adding a dual weak pigeon principle to S12 or other theories, and he demonstrates that the approximate counting is already strong enough to prove many combinatorial statements. We want to do something similar with the weak rank principle, and so we hope that it suffices to prove theorems where the rank considerations are used, but it's enough only to have an approximate notion of rank. So we build our theories in the following way. We take a theory for constant depth reasoning, like B0. We add an axiom about the mod P function, for the existence of mod P function. And then we add an axiom about the rank principle on top of that. So as such, these theories should be weaker than theories considered so far for bounded for linear algebra. So this program was started by Cook and Soltis by defining linear algebraic theories, and they proved many hard matrix identities in them. And then the work of Tsameret and Hrubesch and Tsameret and Cook used the theory VNC2 to prove properties of determinant and hence those hard matrix identities. We hope our theory is possibly weaker because it extracts the rank principle as an axiom, and all the rest is as I said, weaker theory. Well, we demonstrate this approach on a Smolensky low bound. We prove that our theory can prove the Smolensky low bound, particularly the exponential low bound for constant depth mod P circuits, computing the parity function. Yeah, I'll finish on that.
Thank you. We have time for questions.
Michal, can you say something about the notion of approximate degree? Or you mentioned some relaxation of the notion.
That's not approximate. It's just a weaker.
Yeah.
It means weaker. Relaxed means weaker to me. For the situation for our formula is more complicated than for formulas like pigeon principle, because our formula has many sorts of variables. It has x variables, y variables, and then because if we need to consider these CNF encodings, it has our z variables and u variables, as we have seen. Each of these variables has 2 or 3 indices. So there is many possible combinations how to, using these indices, how to define a notion of degree. and it's quite difficult to guess which one is the correct one. And a lot of work in the paper goes into that. So it is based, the degree is based on the indices and different sorts, and it's not obvious from the start which indices should play the significant role for which sort.
Thank you.
So for the hardest of circuit lower bounds, how weak can the circuit class be? Is that like is it zero parity also?
How weak can the circuit class be? So we show low bounds for polymerized circuits, but we try to obtain results for AC zero circuits as well. We know, for example, if the proof system is weaker, like resolution, then the results of RAS already, the circuit which is used there, well, it has unbounded fan-in, but it is like just depth 2 circuit or something like that, I think. But it has unbounded fan-in. That's maybe a drawback. We have a fan-in 2 always. So we care about our circuits to be Boolean. We don't want unbounded fan-ins. But in this paper, we prove it for just polymerized circuits, the low bound.
And follow-up on this. Was your function given to you? The function for which you transfer circuit low bound into the proof system? Was it given?
By a truth table. By a truth table. So we have a circuit, and we have a kind of template for a circuit. So each gate there's a variable saying what the gate is, where it is wired, and for each gate there is another variable which says what is computed, but on each input. So these variables are indexed not by a gate and by an input to the function f. So its exponential setting is the same setting as in Radproof. So yeah, if the number of input bits to function is n, this formula already is exponentially larger. But this is standard. The Dolman is, of course, exponential in our case in the size of the formula.
Also, n is going to be the size of the truth table?
No, it's like two exponentials, and one is like exponential in the other. Like the formula is exponential, and then it's exponential in that. So what did you ask about the root of the?
Yeah, so I just was curious. The notation was the function was from n bits to.
Yeah, from n bits to
the lower bound was to the n to the omega 1.
to the omega 1. Yeah.
But is it the same n?
Uh,
Or is it like the size?
This is for the size of the whole formula. This n in the low bound, and yeah, it's for the size of the formula.
Maybe we can take this offline.
Mhm.
Let's thank the speaker again.